Hey, now I will explain the effective stress in soils. But I think you guys roughly understand of the what is the effective stress, right? So this is the stresses acting on the interface between soil particles. So, but I think it is still unclear what it is. So hope that after today's lectures, you will be able to understand the effective stress concept and then calculate total stress and effective stress and port pressures in the soils. Today only cover the first learning outcomes. So at first, let's discuss about the total stress and pore water pressures. The soil is a particulate materials, and if we consider it at a scale of the individual particles, the forces are transmitted through the soil by stress at interparticle contacts, both normal and shear tangential directions. And forces are also transmitted through the soil by any pressure in the pore water and pore air, which is the total stress. This is a bit different point of view. If we consider soil elements large enough to contain many soil particles, it is possible to consider soil as a continuum materials. Actually, it is a discontinuities. But to solve some stresses and forces, we assume our soil is a continuum materials. So we can consider total stress acting on the surface of the elements as a total forces transmit across the face of the element. And these total stresses can be include the both normal and shear stress. So unlike solid mechanics, our soil mechanics, we use a sign convention that compressive normal stresses are positive. This compressive force is the positive because the normal stresses are mostly compressive in geotechnical engineering. So if the ground surface is the horizontal and soil has the unit weights through the soil layer, gamma 1 and gamma 2, we can calculate vertical normal stress, sigma V at a certain depth, jet, from the ground surface. There will be no shear stress acting on the vertical cylinder surface. It means only vertical and horizontal stresses are available, which is the principal stresses. So this vertical effective stress is self-weight of the soils above the certain points. Right now is a gamma 1 times Z1 plus gamma 2 plus Z2. This is the vertical stress. Total normal stress, total vertical stress, total stress are the same terminologies. So total vertical stress indicates total stress and then stress directions. But sometimes we can just say total stress, which is the summation of the weight of all materials above the certain depths, which includes soil and water. So vertical stress at this point, the unit weight of soil, for each layer times soil depth for each soil layers. That's all. But in this case, we don't know about the water informations. So I don't know whether This gamma 1 is the saturated or total or dry. So vertical stress is at this point unit weight of the soil layer times the each layer soil depth, which is the vertical stress. And then this stress distribution called geostatic stress conditions. Our ground conditions is the at rest, doesn't move, right? And then our soil conditions create certain pressures depends on the soil's unit weight, right? This is the geostatic condition, geostatic stress. Let's consider for uniform soil with the total unit weight, where the ground surface is the horizontals. And then at this point, our vertical total stress is gamma times depth. Total unit weight means we don't know about soil's moisture conditions. Probably it is the wet conditions. If let's say this soil is the totally dry conditions, probably these uh, questions tells me the gamma is the dry gamma D. And let's say we assume our groundwater table at the ground surface, probably this soil is fully saturated. So unit weight will become gamma set, saturated unit weight. But we don't know right now, so we just call it total unit weight. The total unit weight times jet is total stress. Let's talk about the pore water pressures. It is the pressure within the water in the void of saturated or unsaturated soils. It is known as the pore water pressure, PWP. Generally, the value of water pressure increases with depth and technically below the groundwater tables. Gradually increased with the triangular shape. The locations where the water pressure is zero is known as the groundwater table, groundwater. If the water is stationary, we learned just before, the water table is the horizontal and the depth is ZW. So the water pressure is the hydrostatic pressures, which is gamma W times water depth, ZW. Water pressures at a certain point is the unit weight of water times the corresponding depths. This is the water pressures. So in general, the below the water tables, the water pressure is positive with the value on the hydrostatic conditions mentioned before. And then while above the groundwater tables, the water pressure is probably negative, which is the also on the hydrostatic conditions. Negative water pressure, sometimes we can call it metric suctions. It is kind of suctions. You suck some water through your straw, which is the negative pressures. Probably attract the soil particle together. So below groundwater tables, the soil probably fully saturated, and above the groundwater tables, the soil probably partially saturated. We say, in other words, unsaturated soils. But let's think about the soil just above the groundwater. It can also be regarded as the saturated condition due to capillary rise, which is the metric suction pressures. That's why the water goes up a little bit more. So this zone is probably saturated, but technically and then theoretically, this zone also unsaturated zone. But in most of the lecture, this trimester for soil mechanics, it is assumed that soil is fully saturated. Let's say if we have a chance to discuss about unsaturated soil, I will briefly explain what is the soil, unsaturated soil mechanics, what is the different things from the saturated soil mechanics. Hydrostatic pressures, we keep discussing on this because it is one of the water pressures. In soil mechanics, which is the pore water pressures. Water is a stationary conditions. The water pressures say hydrostatic pressures. So, our soil mechanics pioneers, Carl Terjagi. Someone pronounced it Terjagi, or someone said Terjagi, but for me, I prefer Terjagi. Propose the concept of effective stress. This effective stress is the normal directions, mostly these normal directions. This effective stress is the stresses transmitted through the soil skeleton only, through the grain contacts and normal direction only. Soil particle, they are contacted each others. In this interface, this is the effective stress, normal directions. Water pressures is the pressures of the water filling in the void spaces between solid soil particles, acting in or around. You jump into your swimming pool. You feel only normal direction? No. This direction, this direction, this direction, this direction, this direction, this direction, any direction, all around directions. So total stress on a plane within soil mass is effective stress, this contact normal stress, plus pore water pressure, which is the force per unit area transmitted in a normal direction across the plane, idealizing the soil to be a solid materials. So effective stress plus water pressure is total stress. What is the effective stress again? The total stress acting on saturated soils. And then it is particularly carried by the water pressures, and the remainder must be entirely carried by soil skeleton through the interparticle contacts. So these water pressures are incapable of sustaining certain shear stress. So only soil particle carries the full shear stresses. So Terjagi, our pioneer of the soil mechanics, proposed effective stress concept to stress minus out water pressures. We don't care about water effects. We focus on only soil particle interactions. It shows that all aspects of the mechanical behavior of saturated soils are entirely governed by effective stress acting on the soil, because these represent the stresses actually carried by soil skeleton only. Sometimes water in the soil particle, which is the pore water, support certain loads. But we don't care about the pore water pressure because this water pressure cannot resist shear force. But in our soil mechanics and geotechnical structures, they need to resist shear behaviors, these kind of things. This is a shear behavior because our soil particle has a specific texture, right? And there's certain cohesions. So that's why they are contacting each other, and then I press this way. So there should be some resistance. This is a shear resistance, shear strength, but water cannot, totally cannot. So when you're dealing with some soil strengths, we mostly talk about effective stress concept. Of course, we have certain situations dealing with total stress, but you need to differentiate it. You need to, you are able to recognize the different situations. What is the effective? What is the total? Something like that. In the our shear strength parts, I can explain how we can differentiate it, effective and total stress. But the examples clearly tells you about, please calculate effective stress and port pressure and total stress. Okay? Okay, this one is also quite a simple examples. I think you can try first and then we can discuss further in our tutorial sessions.